This lesson will involve confidence intervals. Now, confidence intervals are a fairly simple thing for individuals to calculate. They can be a little bit nuanced when it comes to interpretation. People tend to confuse the confidence level with the probability and what it's saying. Okay? But they're also straightforward in the sense that not only are they pretty easy to calculate, but they're profoundly powerful and important once you understand what it is they're actually saying and not saying, which is why it's so important to understand how uh, how to interpret them. Okay, so this should be a fairly quick lesson. Let's start off with a definition. What is a confidence interval? Well, a confidence interval is nothing more than a range of values, right? Likely to contain the mean at a predetermined level of confidence. So it's a range of values likely to contain the mean at a predetermined level of confidence, which is the definition you can find anywhere. You could probably just Google it and it'll come up. What is a confidence interval? It's a range of values likely to contain the population mean at a predetermined level of confidence. I'm assuming that's exactly what would come up. Okay. So there's three things we need to break down in there. We need to break down a range of values. We need to break down likely to contain the population mean. And we need to break down at a predetermined level of confidence. Okay, so let's start with that. A range of values. What does that mean? Okay, well, a range of values is nothing more than like how long does it take you to go to get home from your best friend's house? Right? Oh, 5 to 10 minutes. Well, that's a range of values. Okay, how long does it take to fly from New York to Los Angeles? Oh, like 5 or 6 hours. That's a range of values. How long does it take to watch a baseball game? Oh, about 2 to 2.5 hours. That's a range of values, right? How long is a good movie? Like an hour, 45 minutes to 2 hours and 15 minutes. Range of values, okay? What's a healthy weight, right? Oh, it's a range, right? I'm 6'2". I think the healthy weight would be something from like 170 to 175, something, right? That's the healthy range weight, right? So let's do this for, quant stuff now. Okay, well, what is the range of the stock price between 100 and $110, right? How many lithium ion batteries are likely to roll off the assembly line and be defective? Oh, between 15 to 20, right? How long is the majority of how long could you expect an 18 to 25-year-old to watch a commercial featuring Lamborghinis in it, right? Oh, 12 to 18 seconds. Okay. These are all ranges of values. Okay. Obviously, the last one you would use marketing. Okay. Uh, because if you want to sell somebody, I don't know, a sandwich, selling a sandwich on TV is not all particularly attractive. But if you put that sandwich or a famous sports player eating that sandwich on the hood of a Lamborghini car, suddenly you have people's attention, even though they're just selling you, turkey. Okay. So all together now, what we have is with a confidence intervals, it's a range of values. We have a lower bound and an upper bound. How long does it take to get home from your friend's house? Oh, I don't know, 5 to 10 minutes. The lower bound, the lower number, that's the 5 minutes. The upper bound or the high, that's the bigger number, right? So between 5 to 10 minutes, lower bound, upper bound. Okay. Those form the endpoints of the interval. So, in other words, how long does it take to get home? Between 5 to 10 minutes. So, what you're saying is it doesn't really take between 4 minutes 3 minutes, 2 minutes, and it probably does not take 11, 12, 13, 14, 15 minutes. It takes between 5 and 10 minutes. Okay, so that is the bounds. That's what binds the interval. That's its endpoints. Okay, its lower endpoint and its upper endpoint. All right, so that's the first thing is a confidence interval is a range of values. The second thing, likely to contain the mean. So it's likely to contain the mean. We believe that this interval really does contain the true, actual, realistic answer of whatever it is we're examining. So, how long does it actually, really, truly take for a United airline jet to travel from Newark Airport to Los Angeles Airport, right? Los Angeles International, LAX. Well, if we estimate that it takes between 5 hours and 6 hours, then we are gauging that the true actual amount of time that it takes to get to Los Angeles International Airport is somewhere in that interval. That's the belief that the true parameter, the population parameter, is somewhere in there. Okay? So that's the second thing. It's a range of values likely to contain the population mean. And then this next part is the one that trips people up sometimes. Likely to contain the mean at a predetermined level of confidence. Okay? Now, let's be clear what we mean by a level of confidence. When you walk into something and when you think something is going to happen, you are confident that it is going to happen, but you don't know if that thing is going to happen or not. Frankly, you walk in, you think something's going to happen, but it either does or it doesn't end up happening. End of story, case closed. Okay. Here's an easy example, right? Take Michael Jordan. I grew up in his era, right? When Michael Jordan went to take a game-winning shot, you were 90% confident that it was going in. You didn't know if it was going to go in. You didn't know if it was going to happen, but you were 90% confident. You were like, Mike's got the ball. He's going to make the shot. This game is probably over. Probably over. But you're confident about it. You don't actually know if it's going to happen until it either does go in or it doesn't go in. Okay? So, as we'll see in confidence intervals, the level of confidence is saying whether it's a 90% confidence interval, a 95% confidence interval, a 99% confidence interval. The level of confidence is referring to out of all the confidence interval, all the times that you could shoot the ball, right? All the times that Michael Jordan takes a shot, what percent of the time does that ball go in? Okay. So, in other words, if you have a 95% confidence interval, that means that out of all the times Michael Jordan takes a shot, 95% of the time it goes in. Therefore, I am 95% confident that he's going to make it right now. I'm 95% confident he's going to make it now because 95% of the time it happens. However, the probability of this one shot going in is either 1 or 0. The probability of this shot right here, right now, going in, the probability of that occurring is 1 or 0. It either goes in or it does not go in. And that's it. Okay? Let me try to make this, make the point another way. Let's say that out of all the flights that go from Newark to Los Angeles, 95% of the time, it takes between 5 hours and 6 hours. So, in other words, if I had to make an interval, right? Like, how long is it going to take this flight that I'm getting on right now? If I am 95% confident that this flight is going to take between 5 and 6 hours, it's because I looked around and said, oh, you know what? Out of all the flights that are ever occurring, all the flights that go from Newark to Los Angeles, 95% of the time they get to Los Angeles between 5 hours and 6 hours after they leave the gate, right? That happens 95% of the time. So I'm like, hey, the probability, it's 95%. This happens 95% of the time. Well, if I said that the probability of this flight taking between 5 and 6 hours to get to Los Angeles, if I said the probability of that happening was 95%, I would be wrong. The probability of this flight, the one that I'm sitting on, the probability of that getting to Los Angeles on time or not is either 1 or 0. It's either on time or it is not on time. Confidence level of a confidence interval is referring to, out of all the flights that happen, what percent of all of those flights are on time? Or what percent of those flights get there between 5 and 6 hours later? It is not talking about my one specific flight right here, right now. Okay. That's an important point when it comes to confidence intervals, because you'd be amazed at how frequently people misinterpret it. Okay. Especially when it comes to Deal or No Deal. If you guys know that game show, it's from a bunch of years ago, but there was a game show called Deal or No Deal where you didn't know they had these briefcases that were closed, and you always had to guess at whether the briefcase had $1 million or 25 cents in them. And people would say, like, oh wow, there's two briefcases with $1 million left, and there's one briefcase that has a quarter, so I have a 2/3 chance of becoming a millionaire. And the answer is no, you don't. In fact, the probability, if you're holding this one briefcase in your hand, pretend my phone's a briefcase, right? If you're holding this one briefcase in your hand, that means that the probability of this briefcase containing $1 million is either 1 or 0. It either has $1 million in it or it doesn't. It does not tell you anything about all the other briefcases in existence. It could be wonderful that there are 20 other briefcases out there that have $1 million in it. Guess what? You don't have it. You only have the one that's in your hand. And the one that's in your hand either has $1 million in it or it has a quarter in it. And that's that. What probability is referring to, probability refers to, out of all the experiments that happen, what percent of the time does your number come up? But it doesn't say anything about what's going to happen this time. This time, your number either comes up or it doesn't. That's it. Okay. Take a coin flip. We know that out of 1 million coin flips, right? Say you flip a coin 1 million times. We know that out of 1 million coin flips, roughly 50% of the time, it will come up tails, and the other half of the time, it will come up heads. So, out of all the coin flips that ever go on, you are 50% confident that you will get tails. However, the probability of you getting tails right now on this flip, this one right now, the probability of that happening is either 1 or 0. You either get tails or you don't. That's the result of what's going to happen. Okay? That's important to remember because that's going to come up with confidence intervals. Confidence intervals, you either get an interval that contains the mean or you don't. Okay? Just as an example, just the last one, I don't mean to, I'm just trying to drive the point home. But take the weather apps that you have on your phones, right? So when you want to, is it going to rain today? And you look at your phone, you go, oh, it's a 50%. Let's make it 60. It's a 60% chance of rain. Okay, what does that mean? Oh, I guess that there's 60% rain today. Well, what does that mean? Nobody's ever gotten hit by 60% of a raindrop. There's no such thing as, oh no, I'm getting 60% of a raindrop. That's more than 20% of a raindrop. That doesn't make any sense. Okay. What the 60% chance of rain refers to is out of all the places in your zip code, all the events that could happen in your zip code, it's raining in 60% of them. So if you take your zip code, think of like 10 places in your zip code. If you think of those 10 places, a 60% chance of rain means that it is raining in 6 out of those 10 places. That's what it's saying. Okay. A 60% chance of rain means 6 out of the 10 places in your zip code are experiencing rain. So therefore, the app on your phone is 60% confident that you will probably be in an area in that zip code that is experiencing rain, even though the probability of you currently being in an area that is getting rained on is either 1 or 0. You're either getting rained on or you're not. That's it. There's no, right? There's no 60%. There's no 60% of a raindrop, right? Now, what that means is out of the 10 places in a zip code, your app is 60% confident that you are currently in a place that is experiencing rain, even though that area where you are, it either is raining or it isn't. The same way that out of all the flights that are going to Los Angeles from Newark, if 95% of them are on time all the time, then we are 95% confident that you will get on a flight that gets to Los Angeles on time, right? If 95% of all the flights are on time, then we're thinking that, all right, I'm 95% confident that you're going to get on a flight that gets there in the correct amount of time. However, when you actually get on that plane and take off, you either get there on time or you don't. And there's no gray area. You either get there within the interval of 5 to 6 hours or you don't. And there's no way around this. Okay. That's how we can understand confidence intervals. Okay. So again, what's a confidence interval? It's a range of values likely to contain the mean, range of values, right? Between 5 and 6 hours, likely to contain the mean, likely to contain the true actual amount of time that it takes to get there, right? At a predetermined level of confidence. So we're going to say, like, oh, I'm 90% confident that I can get to California in 5 hours and 6 hours. Okay. Okay. If we understand that, we understand most of what there is about confidence intervals. The only other thing to do about confidence intervals is figure out how to calculate them, which is just something we're going to do on our whiteboard. Okay, so for a confidence interval, the one and only question I ask myself when it comes to making a confidence interval. So if I have to actually calculate a confidence interval, the one and only question I ask it myself is, do I know the population standard deviation? Okay, AKA sigma. Do I know the population standard deviation? Okay. If the answer is yes, then we work with the z distribution. We work with the Z distribution. Oh, I should have put yes here. And if the answer is no, then we're going to work with the T distribution. Okay. Now, just to be clear, when it comes to confidence intervals, the three most common levels of confidence are 90%, 95%, and 99%. Okay. The confidence intervals that everyone uses, you use a 90% level of confidence, a 95% level of confidence, 99% level of confidence. What that is out of all the intervals you could create, every time you could, take a shot, what percent of the time will you make your shot, right? So you want to be 90% confident, 99, 95% confident, 99% confident, okay? So the Z distribution, if you ask yourself, all right, so I have to make a confidence interval. All right, fair enough. Confidence interval. Do I know the population standard deviation? If you do know the population standard deviation of whatever it is you're working with, if you know the population standard deviation, if you say yes, then this becomes your formula. X bar plus minus Z times sigma over the square root of N. Okay. Now, just a tip, right? If you're working with the Z distribution, what I'm about to write here, what I'm about to write is only true for this side. So for this half, right? I'm going to give you the values of Z. This is only for this left side. So I'm going to make a confidence interval. Do I know the population standard deviation? If the answer is yes, then for a 90% confidence interval, Z is 1.65. And if you're working with a 95% confidence interval, Z is 1.96. Okay, that's only for over here. So in other words, confidence interval. Do I know the population standard deviation? If the answer is yes, 90%, 1.65 would go right here. If you're doing a 95% confidence interval, 1.96 would go right here. Okay, so let's do an example of that. Let's say, hey, JP Morgan Chase. JP Morgan wants to know the, I don't know, average GDP growth. The average GDP growth of the 2020 decade. Okay. So they take a sample. They take a sample of what? Let's say let's do quarters. So a quarter is 3 months. Quarter is January, February, March. And then that's quarter one, right? Quarter two is April, May, June. Q3 is July, August, September, and Q4 is October, November, December. Okay. So let's say that JP Morgan wants to know the average GDP growth of the 2020s. Okay. So let's say they take a sample of, I don't want to confuse you guys. Well, we could do this. They take a sample of All right. Okay. So I paused the video just quickly because I wanted to do a different example. I didn't want to confuse viewers by trying to calculate how many quarters have passed and all that stuff for our sample size. So let's just start over real quick. Let's say you work for you work for a concert hall. Okay. So suppose a concert hall where event planner wants to gauge how many people will show up for a popular performer's concert. Okay. So what they do is they look. So in other words, there's a big popular musical act coming to town, and you want to get an idea of how many people are going to be showing up to this concert hall. Okay. You want to know how many people are showing up to see this singer because you want to know how to plan for parking, food, uh, you know, t-shirts, merchandise, all those kinds of things. Okay. You want to gauge how many people are going to show up for this particular concert. Okay. So what's the first thing you should look at? Well, you should look at the past, you should look at the other shows on this tour. And you see that on average, 21,540 people attend with a population standard deviation of 357 people. Okay. Then we'll say there were 25 prior shows. At the 95% confidence level, create an interval likely to contain the true amount of people who will attend. Okay. So you're an event planner. You want to gauge how many people are going to show up for a popular performer's concert. What you do is you look at the other shows on this tour. And we said there's 25 of them. You look at the other 25 shows. On average, 21,540 people have attended with a population standard deviation of 357 people. As I mentioned, there were 25 other shows. So at the 95% confidence level, create an interval likely to contain the true amount of people who are coming to this show. All right, first question, confidence interval. when you're making a confidence interval, there's one and only one question you ask yourself, which is, do I know the population standard deviation? In other words, do I know sigma? Well, I just said the answer is yes. You absolutely do know the population standard deviation. How do we know that? Because how do we know that how do we know the population standard deviation? Because in the question I said we know we have a population standard deviation of 357 people. So I said that you know the population standard deviation, but also if you're looking at every other show that has occurred on this tour, right? In other words, you're looking at everything that's happened on this tour, then by definition, that is the population because that's the entire set, right? When there's a musician's tour, it kicks off and they go and they play all their different shows. Well, if you're looking at every single show that came before this one, then you are looking at the entire set, and that would be the population. So therefore, you have the population standard deviation. Okay. So when it comes to making a confidence interval, do I know the population standard deviation? And here the answer is yes. So what is my formula? My formula is x bar plus minus z times sigma over the square root of n. Okay, so that's the first thing. This is my formula. Second thing to do, all right, the 95% confidence level, right? 95%. What's 95%? Well, if I know the population standard deviation, 95% says it right here, right? 95% z is 1.96. So I know Z 1.96. Okay, the only thing left to do here is to simply fill in the other variables and calculate correctly. Okay, so X bar, what's X bar? That's a sample mean. What is my sample mean? I said that on average, right, the average is 21,540. So 21,540. That's my average. Z 1.96. I could just do that. 21,540 plus minus 1.96 times sigma 357 over the square root of 25. Okay. So the only thing left to do here is calculate correctly and to follow the order of operations. So we actually go right to left, top to bottom here. It's kind of just a funny thing of the formula. It's an idiosyncrasy, right? So start with the parentheses. Where in the parentheses? Start with the square root. Square root of 25 is 5. 357 divided by 5 is 71 and a half, or 71.4, excuse me. Okay. So then 71.4 times 1.96 is 139.9, which is really 140. Okay. The only thing left to do now is calculate the lower bound and the upper bound. We have 21,000, 540 minus 140, which is 21,400. And then we have 21,540 plus 140, which is 21,680. So, what this is saying is that I am 95% confident. I'm feeling good, right? I'm 95% confident that at this concert, the one that's coming to my hall, there will be between 21,400 and 21,680 people who come. Now, that means that there could be 21,410, 21,415, 21,500, 21,312, right? Oh, no, sorry, 21,512. Okay. It means there could be a lot of combination, a lot of different values for the amount of concert goers that fit into that interval. Okay. I'm 95% confident that there's going to be between 21,400 and 21,680 people who show up. But the probability of that occurring is either 1 or 0. There either will be 21,400 to 21,680 people who attend, or there won't be, right? If 20,300 people show up, 20,300 people show up, that's less than this number. That would be out here, which means I was wrong. My estimate was off. If 23,000 people show up, hey, that's great news. We're really busy. But my estimate was off. Maybe we don't have enough hot dogs or parking or whatever for them, right? But what I'm doing, my best estimate, is that I think there's going to be between 21,400 and 21,680 people who attend. That's what I believe. Okay. However, the probability of me being correct is 1 or 0. I'm only 95% confident that that's going to happen. Okay. Just as an aside, if I decided to change, if I said, all right, let's make a 90% confidence interval, right? So, in other words, if I said at the 90% confidence level, the only thing that would change would be this number here, okay? Rather than having 1.96, I would have 1.65 there, okay? That's the only thing that would happen. This would be 1.65. Why? Because I mentioned above, right? 95%, 1.96. 90%, 1.65. Okay, so that's just what I would do there. I would have to substitute in, right? I initially said I was doing a 95% confidence interval. But if I'm doing a 90, I would just do 1.65 for Z instead of 1.96. I would just be doing 1.65. That's the only change you would do. Okay. That, again, that's if you know the population standard deviation. If you don't know the population standard deviation, we have to do something different. Okay. So back to the drawing board. Confidence interval. Do I know the population standard deviation? If the answer is no, we're going to work with the t distribution. That's x bar plus minus t times s over the square root of n. Okay. In order to get t, to get the value of t, you need the level of confidence which is 90%, 95%, or 99. But in practice, it's really 90 or 95. That's the ones that most commonly work in business, economics, and finance. And then you need something called degrees of freedom, which is n minus k. Okay. N minus k. N is the number of observations, and K is the number of samples. Okay. N is the number of observations. K is the number of samples. So if you were looking at, say, a basketball player, this basketball player plays, you know, 10 games in the first season and 15 games in the second season, then how many observations do you have? You would have 10 plus 15. You would have watched 25 games, but there was two samples because there was season one and season two. So the degrees of freedom would be 25 minus 2, 23. Okay. That's degrees of freedom. When it comes to our confidence intervals, let's try to do one now where we have to use the t distribution. Okay. Because we're gonna have to go back into our ZT and F distribution here. Okay. So let's say I'm just trying to think of an example to do for us, right? What it make an easy one, stock prices. We want to know the future stock price of Home Depot. We take a sample of 16 days. Now, obviously, this is going to be a sample and a sample standard deviation because Home Depot has been around for longer than 16 days. So this implies we'll be working with a sample. Take a sample of 16 days and find out, we discover that Home Depot has an average stock price of, I'm just completely making this up, $68 with a sample standard deviation of $24. At the 95% level of confidence, create a range of values likely to contain the mean. Okay. So again, we want to know the future stock price of Home Depot. We take a sample of 16 days and discover that it has an average stock price of $68 with a sample standard deviation of $24. At the 95% level of confidence, create a range of values likely to contain the mean. Okay, so again, what's the one and only question we ask ourselves when we're making a confidence interval? Do I know the population standard deviation? If the answer is no, we're going to work with a t distribution. Well, do I know the population standard deviation? The answer is no. I don't know the population standard deviation because I only know the sample standard deviation. Well, if I only know the sample standard deviation, I don't know the population standard deviation. So that means that I need to work with the t. That means that my formula will be x bar plus minus t times s over the square root of n. Okay. That also means I need to get t. Okay. So what's t? I don't know. In order to get t, I need two things. I need the level of confidence, that's 95%, and I need my degrees of freedom, n minus k. What's n? Well, n is my sample size. I took a sample of 16 days. So n is my sample size, 16. How many samples did I take? Right? K is the number of samples. How many samples did I take? Well, I took one sample, so 16 minus 1 is 15 degrees of freedom. Okay? So my degrees of freedom is 15, and I have 95%. All right. So if I know that I have 15 degrees of freedom and I have a 95% level of confidence, what I do is I go to my t distribution. Okay. So I'm going to stop sharing the whiteboard for a minute. And then I have to go to my t. Okay. So once I'm back over in my t now, okay, remember area under the normal curve, this is the z distribution. Page 1 is the z. But then if we go down to page 2, you see, oh, it says students t distribution. That's the t distribution. This is where you go for the t's. Then you might notice on the left-hand column, df, degrees of freedom. It goes 1 all the way down to 35. And then on the right-hand side, it picks up again, degrees of freedom, right? It says df, degrees of freedom, 36 down to 70. And then on page 3 of the PDF, it goes from 71 to infinity. Okay, it goes 95, 96, 97, 98, 99, 100, 120, 140, 60, 180, 200, then infinite. Okay, we'll get to that later on, those degrees of freedom. But for now, we're just starting off. So we have 15 degrees of freedom and 95% level of confidence. So you might notice across the top it says confidence interval 80, 90, 95, 98, 99, right? And then it does it again on the right-hand side for that column, that block, if you will. And then it has it on page 3 as well, 80, 90, 95, 98, 99, okay? So confidence interval, we have a 95% level of confidence. And now we need to just scroll down until we get to 15 degrees of freedom. So let's go to 15 degrees of freedom, right? 15 degrees of freedom. And then 95% level of confidence. So 95% level of confidence, 95%, 15 degrees of freedom, right? 15, 95%, 95%, 15, 2.131. Okay, 95% level of confidence, 15 degrees of freedom, 2.131. Okay. That number is what I'm going to put right here. So T is 2.131. Okay. I got that because I did 95%, 15 degrees of freedom. That gave me 2.131. The only thing left to do now is plug it in. So x bar plus or minus 2.131 times s over the square root of n. Okay, x bar, what's my average? Well, my average stock price was 68, right? So $68 plus minus 2.131 times S, the sample standard deviation of 24 divided by the square root of n. What's my sample size? My sample was 16 days. So square root of 16. Okay. At this point, it's pretty straightforward, right? We just go to the parentheses first. We go right to left and bottom to top. So start in the parentheses. Where? With the square root. What's the square root of 16? 4. 24 divided by 4 is 6. All right. Okay, that's the first step. Now the second step. 68 plus or minus 2.131 times 6 is 12.786. I'm going to round 12.79. Okay. And then the only thing left to do is calculate my lower bound and my upper bound. You always want to have the smaller number come first too, right? So 68 minus 12.79 is 55.21. And then my upper bound, 68 plus 12.79 is 80.79. Okay. So again, based upon these results, right, based upon an average stock price of $68, a sample standard deviation of $24, and if I took a sample of 16 days, I am 95% confident that the future stock price of Home Depot will be between $55.21 and $80.79. Now, will it be? I don't know. I have to wait to see if that actually happens. If it does happen, right, if the stock price is $60, hey, then I was right. The probability of that occurring was 1, right? It happened. If it turns out that the stock price is $130 or $40, it's outside the interval. So I was wrong. Okay. But what this is saying is that I am 95% confident. I'm confident. I don't know if it's going to happen. I'm only estimating that it's going to happen. I'm 95% confident that the future stock price of IBM, of Home Depot, will be between $55.21 and $80.79. Okay. So to wrap it up, because that's all there is for confidence intervals. Okay. Confidence interval is a range of values. We have a lower bound and an upper bound. It's a range of values likely to contain the population mean at a predetermined level of confidence. Okay. It's always 90 or 95%. Okay. Sometimes it's 99, but usually 90 or 95%. Okay. So since we're working with 90 or 95% for the level of confidence, we know that that's what we're expecting to happen, right? We feel good. We're confident about it. But the probability of it happening is either 1 or 0. It either happens or it doesn't. Once we understand what it is we're doing with confidence intervals, then the only thing left for us to do is to actually calculate them. Okay. In order to actually calculate them, the one and only question you have to ask yourself, the only thing you do when calculating a confidence interval is, do I know the population standard deviation? If the answer is yes, yeah, you know what? I do know the population standard deviation. I know sigma. If the answer is yes, then this is your formula. X bar plus minus Z times sigma over the square root of N. And for a 90% confidence interval, Z will be 1.65. For a 95% confidence interval, Z will be 1.96. However, if you go to make your confidence interval, right, you understand what it is. You understand it's a range of values likely to contain the mean and a predetermined level of confidence, right? If you go to calculate your confidence interval and you say, hey, do I know the population standard deviation? You go, I don't think so. I don't think I know the population standard deviation. I only know the sample standard deviation. Well, if that's the case, then you have to work with a t distribution. You have to work with a t distribution if that's the case, which means that you have to do x bar plus minus t times s over the square root of n. If that's what you're working with, you need to get t. And in order to get t, you have to know both the degrees of freedom and the level of confidence. You have to go into the student's t distribution and you have to match up the confidence interval level, right? 90 or 95%. You have to match up the level of confidence with the degrees of freedom 1 to 35, 36 to 70, or 71 down to infinity. Okay, you have to match those up. But that's all there is to it. Once you match up that confidence level and the degree of freedom in the t distribution, once you align those, then again, once you have t, you just simply plug t right in here, and then you have x bar plus minus t times s over the square root of n. Okay, so again, do I know the population standard deviation? If the answer is yes, this is your formula. If the answer is no, this is your formula. And that's all there is to confidence intervals. Okay. So that will conclude our lesson on confidence intervals at this time, and we'll be moving on to one sample hypothesis tests.